Hello, and thank you for joining me today as we continue our discussion on chemical kinetics. Today we're talking about second order reactions, and we're going to talk zero order as well. So last time we talked about first order, these are second order. And in a second order reaction, the rate is dependent on a reactant raised to the second power. So one reactant raised to the second power. These are called second order reactions, which means your rate law then becomes your rate is equal to K times concentration of A squared. And this is our concentration, second power squared there. So if we're looking at solving this for concentration of A, we now know that the rate is equal to K times A squared. And your initial other rate that we talked about previously was your change in concentration over time. So I can set these two equal to each other, so I get K times A squared, which is equal to negative change in concentration of A all over T. I can then set this up so that my concentrations are both on one side. So I can multiply, I can get negative KT on this side, multiply both sides by a negative T, and divide by A squared, concentration of A squared. That's going to land me here, where I get change in concentration of A over A squared equals negative KT. Okay, so we're going to have this situation, and then equals negative KT. Using some calculus, we can rearrange all this, and we end up with 1 over your concentration of A equals 1 over concentration of A naught plus KT. This is going to be your integrated rate law for second order reactions. This is the one that you need to write down. This is where we end up. So 1 over concentration of A equals 1 over the initial concentration plus KT. That's going to be your real important equation. This is going to create your linear relationship. So this is going to be the 1 over concentration A is Y equals mx is going to be K and T still. So M is K, X is T, and plus 1 over your initial concentration of A. Concentration of A. So it sets up like this. This is your Y equals mx plus B. That's how that's all going to look. So we're going to use this bottom equation, or this equation here circled, and we're going to be able to solve for some different variables. If we look at this in a graph, so an example of the decomposition of nitrogen dioxide. This is looking at your concentration change. This graph is showing you the natural log of your change in concentration, or natural log of concentration. Notice how the line is a curve. This one is taking 1 over your concentration. And notice, because your concentration is decreasing 1 over, it's going to make it go up. But this is a linear line. So this is linear for 1 over your concentration, not natural log of concentration. And it's going to be based on this reaction here. Okay, so this equation here is going to yield that situation. The 2 comes from, if this were a full O2, we would have O2 plus 2NO comes from 2NO2. So this is squared because of this 2 out front here. That's my reactant squared. Okay, but that is your second order reaction. And the important piece is you know that this creates a linear graph. 1 over the concentration is linear. Linear graph. So second order is 1 over the concentration equals a linear graph, as opposed to the natural log of the concentration, as in first order. Okay, but that is second order information thus far. That is where we're going here. All right, and the last little bit we're going to get to. So we can use this. We can also solve for half-life like we did with first order. So in the case of half-life, we're using this same equation, 1 over the concentration equals 1 over your initial concentration plus kT. And with a half-life, I need to get my initial concentration, half of it. So 1 over concentration of A naught over 2 equals my 1 over concentration A naught plus kT to the 1/2. I can solve this all for t to the 1/2. So to get t by itself, I have to subtract this to the other side. So I have 1 over concentration of A naught divided by 2, which is equal to 1 times 2 over concentration of A naught. And so that's where we're going to flip that. So we get 2 over your concentration of A naught equals 1 over concentration of A naught plus kT to the 1/2. So if I subtract my 1 across, so I take 2 over concentration of A naught, because my denominators are the same, I can subtract those, equals kT to the 1/2. And so I get 1 over concentration of A naught equals kT to the 1/2. And I can then divide by k. And so I get t to the 1/2 equals 1 over concentration of A naught times k. There is your half-life equation for second order. This means, because this concentration is in here, instead of just being natural log of 2 over k, because concentration is in here, your half-life is a concentration-dependent quantity in second order reactions. So this is really important. I'm going to show you how to use this in an equation in the next video, but this is the equation we're going to use for half-life of second order reactions. The last little bit today, we're going to talk zero order. There are some reactions that are independent. The rate is independent of concentration of the reactant. So it doesn't matter what my concentration is, my rate is always going to be the same. In this case, your rate is going to be equal to K, which makes life really easy. So rate equals K in these reactions. These are zero order reactions, and these are linear in concentration. Okay, so my rate's going to be here. My concentration is going to be linear all the time. Concentration over time is going to be linear. That's going to be my K. All right, that is today's video. Thank you for joining me. I look forward to seeing you tomorrow as we continue discussing chemical kinetics.